Hi, this is Brandon,
I'm Ben.
and we are presenting DES modeling for demand forecasting. So, what is demand forecasting and what is DES? Demand forecasting is the process of predicting future customer demand for a product or service based on historical data, market trends, and other relevant factors. It is a critical tool in inventory management, supply chain planning, and business strategy, helping organizations optimize resources and meet customer needs effectively. Discrete events systems models a system as a series of discrete events that occur at specific points in time. In application to demand forecasting, discrete event system serves as a valuable tool for modeling and analyzing the dynamic nature of demand and its impact on inventory systems. By simulating real-world events such as customer orders and stock replenishments, DES incorporates variability in demand patterns and lead time, enabling businesses to evaluate the effectiveness of forecasting methods and inventory policies under different scenarios or current events. It provides into key performance metrics, allowing organizations to optimize reorder points and order quantities based on forecasted demand. This approach should, in theory, enhance forecast reliability and support strategic planning for managing uncertainty in supply chain operations. Using outside research, it was found that there is an existing model that simulates demand forecasting. From the IEEE article, Simulation Evaluation for Efficient Inventory Management Based on Demand Forecasts, EOQ, or Economic Order Quantity Model, is a model that uses efficient inventory management, optimal order quantity, leading to deriving appropriate lead time cycles, safety stock, and order placement points. Safety inventory prevents risks associated with the occurrence of shortage inventory events during lead time periods. It is also used to reduce inventory costs in order to calculate appropriate orders and reduce inventory maintenance costs, inventory quantity, etc., compared to demand. Another technique was data analysis using data mining technology. It was used to analyze past data to grasp special rules and patterns of data. And a third model would be, or technique or model, would be the ARIMA model. The ARIMA model is a demand forecasting technique. It is a mixed model that combines the auto-regression model and the moving average model. The auto-regression model is a machine learning model that uses past data to predict future values in a sequence, while the moving average model is a model that models the univariate time series. It specifies that the output variable is cross-correlated with a non-identical to itself random variable. Using this model helps supplement the EOQ model to help predict future demand.
So, what are the practical applications of demand forecasting? Demand forecasting is used by companies so they can forecast how much of a product they should order each time they need to order their products. So, if you're a company, you obviously want to have inventory for the demand that your customers are going to have. So, it's good to have a demand forecasting system so that you can predict when and how much you are going to need to order a product. This helps by being able to save money by preventing overstocking and paying for a lot of warehousing space that you really don't need if you can time your programming correctly to be able to order things on time every time. Some examples of this is IBM Planning Analytic, Oracle Fusion Cloud Demand Management, SAP Integrated Business Planning for Supply Chain. These are all some industry examples of demand forecast software that businesses are able to use to forecast the demand for their products. And these products are pretty advanced. Some of them use AI, if not all of them. And finding technical information regarding demand forecasting is pretty hard. And a lot of this is because it's proprietary information or trade secrets to these companies, because this is how these companies make money. They don't want that to be out on the internet and be open software for people to use and modify on their own.
Anyway, back to the IEEE article. From the IEEE article, the problem statement is that a company is using an EOQ model. However, it can only grasp the accurate lead time and understand the proper order quantity. It cannot accurately predict future demand. This is due to frequent fluctuations in demand, causing company to not supply in a timely manner in response to demand. The proposed solution to this problem was to use the ARIMA model. The EOQ model, by using the ARIMA model to supplement the EOQ model, the EOQ model will be further improved to predict demand forecasts. And the justification for this is that by allowing the EOQ model to predict demand forecasts, a company should be able to reduce inventory management costs and reduce inventory shortage rate. The company will overall be able to meet customer demand timely. So why is the ARIMA model so important? As previously mentioned, the ARIMA model can predict the demand pattern based on past data. This is thanks to data mining. The ARIMA model, using the past data, can use a quantitative method to grasp the appropriate inventory quantity. As a result, the past data is used to ultimately find demand patterns to predict future demand quantity. With that said, implementing the ARIMA model to the existing EOQ in the company would help enhance its capabilities further in performing its tasks. Has this state-of-the-art model been verified to work? Why, yes it has. In their simulation, the demand forecasting algorithm starts with orders that are placed when inventory drops below a dynamically calculated reorder point derived from the average demand during lead time. The model adjusts reorder points and calculates optimal order quantities within each cycle, ensuring adaptability to fluctuating demand. Inventory levels are updated upon order receipt, and the simulation runs for a 53-week period, tracking key metrics such as inventory shortages, shortage periods, and average order quantities. At the time, the company operated at a 60% service level in its existing EOQ model, resulting in a high inventory shortage rate and challenges in managing inventory. At that level, 4 inventory shortage counts were recorded in an inventory shortage period of 22 weeks. When using the developed EOQ model by implementing ARIMA, the service level jumped from 60% to 90%. At 90% service level, the period of shortage rates was 4 weeks, and the inventory shortage count was 1. You can see the difference between the two service levels. By jumping inventory shortage rates reduced drastically. As a result, the developed demand forecasting model was reduced by 53%. The developed model showed that predictions through the ARIMA forecasting method overcame the existing EOQ model difficulties.
Okay, so our unique and proposed idea is basically that we wanted to use a simple finite state machine to model a demand forecasting system. So as we can see here, we have a basic 5-state finite state machine. We start at state 0. That state 0 is the state initializer for our system. We are basically going to create a set of historical data as our mock data for sales, and that data is going to have 1 data point per month, when we are going to be able to feed that into our system. Our system is going to look at that and create a order plan for a 12-month period. So we're going to have orders for once a month, and that is going to be able to be our base plan that we're going to work with. We're going to feed that into state 1, and that is when we are starting to process our mock current sales. So our mock current sales would be At the end of the month, we're going to collect our sales, we're going to put it into the system, and we're going to basically decide what we need to order for stock. Once we have that, we can go to state 2. Now, state 2 is where we have to decide what method we want to do to order. So we have 2 ordering methods. The first one is that we can choose whatever batch size we want, and we're doing an order once a month. So with this, we're able to do a batch size of 5 items. We're able to do 15, 25, 35, whatever it is. We can choose any number we want. Method 2 is basically saying that our batch sizes are static. So we might talk to manufacturer and they say that we need 15 products. And they'll say we only sell or we will only manufacture in batches of 20. So if we need 15, we're going to have to order 20. If we need 35, we're going to have to order 40. So basically, we have these 2 methods. We have a way we can determine it in the code just by true or false statement. And once we have that, we're able to create or modify our demand forecast orders. So we have that historic data and the historic orders, and we look at those historic order predictions, and we say, hey, there's some inconsistency between our current data and our historic data. Let's adjust our order predictions right here so we're able to provide sufficient stock for the incoming demand. So we can do that, and what we do is we can place our order, and then we go to state 5, and once we have state 5, we can update our current stock and reset our PTO tags. So simulation, we have pretty simple simulation where we're just using some basic MATLAB code. Just very basic. We use 3 main files, and we have a live script and non-live script version of our main file, so that's the only difference between these 2. So for state 0, this is basically what goes on behind the scenes. So same thing as before, read historic data, generate order plan, track expected data, and then we can calculate if our demand is met. So if we look over here, what we can see is that we have our historical data blue. So this just basically means that this is our sales in the past. And then what we can do is we can look at that and we can say, okay, let's have a predicted order that we're going to have. So we're always able to have stock for our product. So we look at this red line. This is what we are going to order so we can stay on top of things. And then we look at the green line, and this is how much stock we have of everything. Same thing up here, same thing down here. Only difference is that we're using method 1 to determine what orders we should have. Right here, we're using method 2. So once we go over to here, we can see if our demand is met. So this black line is basically representing how much demand we have to how much stock we have. So there's a red line at our 0 Y level, and that basically means that if we're at that red line, we have exactly as much stock in an order cycle as we do demand. So as we can see here, we always are above our demand in this scenario. Right here, we have a significantly above average stock compared to our demand. And we go over here into method 2. We can see it fluctuates a little bit more. Sometimes we're pretty high, sometimes we're at 0, but we're able to stay at least at our demand level. State 1. So state 1 is where things start to actually go into demand forecasting in live time. So basically what we're going to do is we're going to simulate retrieving current sales. So the way we do this is basically set up this array right here, and what we're going to do is we're going to look at one number at a time for this. So what we're going to do is we're going to say, okay, first number in the array, 1. So we're only going to look at that. We're going to say this is our current sales from the month. We're going to put it into a function and say, what should our sales for the next month be? Once we throw it into a function, we're going to get our order for that month, and then we're going to move on to the next month and say, okay, now we have a sales of 2. Subtract this from our inventory and look at the historic data. What do we have to order? And so on and so forth. We're going to keep doing that, and that's basically state 1. We're only doing 1 month at a time in state 1, and before we can go to the next month, we have to go through all the next states. So state 2, its primary functions here is basically we're going to determine which method we want to use, and once we get which method we want to use, it feeds back into state 2, and what we're going to do is we're going to have our order quantity, and we're going to place that order. So state 3 is our method 1 state. What it's going to do is compare the historical sales to the current sales, say, hey, there's something up here, let's make adjustments, or hey, this looks good, this matches our historical sales, let's keep what we already have for our orders. And once it does that, it'll feed back into state 2. Similar for state 4. State 4 is going to do almost exactly the same thing, except for we're using method 2. And state 5 is where we're going to just do some inventory. We're going to check what's going on. We're going to make sure we have accounted for all our inventory and that we did the appropriate orders with all our stocks. And we're going to restart our countdown to the next order, which just basically means we're going to say we're done month 1. Let's wait until month 2 before we can do our next order. And that's when we would end up going back to state 2. All right, so here's our results. So before we look at it, this on over here on the left with the magenta and cyan colored graph, that is our graph that shows what the difference between our historical data and current data is. So basically what this is representing is, okay, month 1, what we are going to have in month 1 versus in the historic versus current data. So current data, we would really only be seeing 1 month at a time or only the previous months. We wouldn't get this full picture until we actually get through the whole entire year. So once we get to item 12 on this list, which would just be December, we're only going to see that current data once we're at the end of December and we get that December data. So this simulation is going to show this as if we went through the entire year. And this is what our orders looked like throughout the year. So same thing over here. We go here. This is method 1. We can see that in the blue, that is what our historic data created an order report for. And we have our red orders right here, so that is our updated order report using method 1. Same thing here, but instead the red data is using method 2. As you can see here, method 2 uses batch sizes of 20. So with batch size of 20, we're only going to have 0, 20, 40, and 60 batch sizes order, versus over here where we have a very dynamic amount of order sizes where we have 5, 30, so on and so forth. All right, so going into results a little more, this is method 1 results. So what we are looking at right here is similar to what we were looking at earlier. So blue is our sales report, so our current data. We go through this. Again, we're only going to see basically what's behind the current month. So if we're in February, we're not going to see what's going on in December until we're at December. But we can see in red what our order report was and what our stock report was based off of those orders. And once we go over to here, we can see that it's not perfect. So what we can see here is that there's a lot of fluctuations between stock availability and demand, and that a lot of times it's a little bit difficult for the system to catch up to the demand, so it goes back and forth a lot. And we can see right here at 9 that there's a big spike in demand overseeding the stock that is available, and that it correlates to that big bump that's over here. And here's our method 2 results. So a little bit similar. So we can see here that our orders are a little bit hard to keep track of, and that's probably due to it being set to batch sizes of 20. And we can see that our stock right in the middle has this big dip in availability. And we can see in our met demand that our demand is often more than our stock availability. And then what we can see right here is that we go back up and there's a bit of a overcorrection there. And now we have way more stock than we previously had compared to demand. So what are the results? As we talked about previously, we had like a bit of an overcorrection here in this specific graph, and then we have below this red line that our demand isn't met. But like, what do we get out of this? So we're able to make a basic order plan using our historical data to fulfill orders, and it's a good start for creating a demand forecasting system. But we really struggle to get a system that is able to dynamically adjust to incoming data and say, hey, this is how we should adapt to a situation, so we're able to produce a more efficient ordering plan. So how we would want to improve this is we believe that Stage 3 and Stage 4 should have some reworking to it, specifically to how Method 1 and Method 2 are handled. So what we found is that we did a very simple analysis in Method 1, Method 2, and what it should probably be doing is taking a more robust look at this data and the previous data and what it expects the future data to be, and look at it in a bigger picture. And with taking all of that into account, we think that we could get a more steady output where we're able to ride this red line or stay above it. And we think that if we're able to get that working, we could also increase the operation scale that this works in. So we are assuming that one order period for us is once a month. So we have 12 total in our simulation. And that is a bit flawed if we were like trying to be like, hey, this is a practical use for our system. So what we would want to do is be maybe upgraded to 52 next, representing like 1 week a year. And then what we could do is we could take that current data that we're creating plans for, and then once we're able to get a bigger picture of like how those plans worked out, what were the strengths and weaknesses, what we could do is we could take that current data in that either successful or unsuccessful order report and feed it back into our historical data and say, let's make a new historical model. Let's make one that's a little bit more accurate to our most recent data that we got. And as a conclusion, we made this model, and we found that one of the big challenges behind it was there wasn't a lot of literature or academic papers or technical details on how to do a model like this. And we felt that this was highly because this is a commercially available product. This is going to be a trade secret that these companies don't want getting out because this is a very valuable tool for them as a business. And but we still feel that making a simple design was pretty advantageous because like we're able to look at it from a very simple perspective, try to figure out what's going on, and like have a more deeper understanding compared to what an industry model would use for like their versions, which most utilize some sort of AI. And we feel like that working on this, we like created like additional documentation or research on how to approach this problem of demand forecasting and how other people in the future should try to approach this problem. And here's our references. Thank you for watching.